work is equal to 0. Therefore, delta E thermal is, 0 plus Q. But since process A is at constant volume, what is Q? Q is, what's the relationship between Q and the number of moles and so on at constant volume? NC delta T. So it's N times C times delta T. But specifically, what C?
Specific.
CB, because it's constant volume. Yeah. Right? Process A is isochoric or isochoric. It's constant volume. See, the volume did not change. So the volume did not change. So NC delta T, but it's CB. Okay. That's good. We're going to go to process B now. Process B. Process B. I will write delta E will equal to how much work is done if the pressure is constant? Remember what the work done in an isobaric process? Negative P times what?
Delta V.
Delta V, yeah. The work done in isobaric, let me put thermal here. The work done in an isobaric process was, the work done is always the integral of P dV, but if P is constant, pull it out of the integral, and you get negative P, the integral of dV, from V initial to V final, so it will just become negative P delta V. Okay. Negative P times delta V. Okay? And then plus what? This is the thermal energy, so this is the work part, and then Q. And what can I write for Q here? N CP, yeah, at constant pressure times delta T. Yeah, thank you. Yeah. And now, I'm going to relate this to this, but before then, I need to get rid of this P delta V. I need to make it something in terms of delta T. But remember, again, the pressure in process B is constant, right? Pressure in process B is constant. So, since, where should I go? So I know that P V equal to nRT, right? If the pressure is constant, it means P delta V is equal to N delta T. P delta V is equal to N delta T. Because any change on the left side has to be from V, because P is constant. And any change on the right side has to come from where? From T, because N and R are constant. So that means, what I'm saying is that P delta V is the same as N R delta T. And that's what I'm going to replace this by that. So in other words, take this equation, now I have delta E thermal will be minus P delta V, but P delta V is N R delta T, plus NCP delta T, NCP delta T. Alright, so now, the change in thermal energy through process B, the change in thermal energy through process A. Is the change in thermal energy in both processes the same or different? The same, because? Yeah.
Because in one of them there's no change in volume, and there's a change in pressure, which means that the temperature is not changing.
Okay.
It's the same.
Same something. Yeah. So let me give it.
Yeah.
Yeah. Let's get. I think I saw other hands. Who wants to give it another shot, and then we'll go. Why is the thermal energy in process A, the thermal energy change in process A, the same as the thermal energy change in process B?
Same temperature?
Same temperature.
Like final temperature?
The final temperature is the same. How about the initial temperature?
Same.
The same. So the change in temperature is the same. Therefore, they start if they have the same temperature initially, it means they have the same thermal energy initially. If they have the same temperature at the end, they must have the same thermal energy at the end. So the change is the same in both cases. So in process A and process B, these delta E thermal, they are equal to each other. So we're going to equate them. We're going to equate this to this. And that's what will give us the result that we're looking for. So let's use it. So we're going to equate this NCV delta T to equal to negative NR delta T NCP delta T. All right, so let's do that. So NCV delta T is equal to minus NR delta T plus NCP delta T, right? Notice the and the delta T, the N, the delta T, and the N and the delta T cancels. And you end up with CV is equal to minus R plus CP, right? And so you get CP is CV plus delta T plus R. So that's the result I wanted to show. Yeah, I might have some more time to do the adiabatic process one, some derivation just to get it out of the way. So Thursday, we will start chapter 20. We will spend about half an hour still on this chapter, or maybe 45 minutes, and then we will start chapter 20. So I'm going to show you the adiabatic process now. Again, we really have two things to work with. The ideal gas law and the first law of thermodynamics. And that's what we're going to use in all of our derivations, plus the definition of whatever process we're using. So, for an adiabatic process, do you remember what was special about it? No heat is entering or leaving, so Q is equal to what? 0. Q? Equal to 0. Good. Let's start with our first law of thermodynamics. I know that delta E thermal is equal to W plus Q, right? But Q is 0. Q is 0. So I have delta E thermal is equal to W. Okay? And I'm going to write this in differential form. So DE thermal, a small amount of change in E thermal is equal to a small amount of work, dW. Now, the change in thermal energy, we wrote it in two different ways, right? The change in thermal energy is related to the change in temperature, which we can always write it this way, NCV dt, or delta T. Again, delta T, I want a small amount of change, so dt instead of delta T. So I have NCV dt for delta E, for DE thermal. For this one, I will write, NCV dt, thank you. NCV dt. And here, a small amount of work, remember it was minus P dV? Because work is the integral of P dV. And as usual, P is, see I have dt here. When I integrate in terms of T, I want to integrate in terms of V, so we need to get rid of the T. So it needs to go away. So P, how do you eliminate P? Use ideal gas law, yeah. Yeah, we kind of exhausted our choices. We used the first law. We have the ideal gas law to use that. So P is nRT divided by V, right? Yeah. So I would have on the left side NCV dt, and this one is minus nRT over V dV, right? you see the and goes away. Let's see. So divide both sides by T, and then both sides by CV. So you will get dt over T is equal to minus R over CV, and then dV over V, right? So, and then what's the next step? What do you think I'm going to do? Yeah, integrate. Yeah, we have a really nice expression looking at us, and so we need to integrate it. So integrate from where to where? From T initial to T final, right? And this one from some V initial to some V final. Right? Both of them will give me the natural log, right? This will give me ln of T, evaluate between T final and T initial, so that's ln of T final minus ln of T initial, which is the same as ln of T final divided by T initial, right? So on the left side I would have ln T final over T initial, and this one I would have minus R over CV ln of V final over V initial, and by properties of logs, if you have something times a log, you have the log of that thing to the power of this, right? So I would have ln of T final over T initial will equal to ln of V final over V initial to the minus R over CV, right? And something to a negative power, I can make the power positive, but flip the fraction, right? Because something to the negative means 1 over. So I can write it as ln of V initial over V final to the R over CV, right? Again, the minus sign, I just flip it. And if the natural log of something is equal to the natural log of some other thing, it means those two things are the same. Okay, so it means the T final over T initial is the same as this. So this is, and I keep looking at the plot, T final over T initial would equal to V initial over V final. And I'm going to, the power here, I'm going to write V initial to the R over CV and V final over R over CV. So V initial to the R over CV, and then R over CV. We will just get one expression that we just need to remember at the end. But I just want to go through the derivation just a little bit. And cross multiply so that we have final on one end and initials on the other end. So we get T final, V final to the R over CV is equal to T initial, V initial to the R over CV. And that's good enough, to be honest with you. But people usually write it as in terms of a new thing called gamma. So they define a gamma, a number called gamma. It's a constant. If you have a diatomic gas, it's a certain number. If it's monatomic, it's a certain number, and so on. Gamma is defined as the Cp over Cv. Just by definition, it's Cp over Cv. So take the specifically the constant pressure divided by the specifically the constant volume, that's gamma. But Cp is Cv plus R, right? Over Cv. And if I reduce this, I get Cv over Cv is 1, and then R over Cv. So R over Cv will equal to gamma minus 1. So R over Cv, gamma 1. And that's what I'm going to replace R over Cv by gamma minus 1. So we get the following expression, Tf, V final to the gamma minus 1 is equal to T initial initial to the gamma minus 1. And then, so this is 1, maybe it deserves a box, but usually it's written in terms of pressure. And in terms of pressure, you would write, instead of T final, what is T final? It will be P final, V final over NR, right? So let's write it that way. So instead of T final, I will write P final, V final over NR, and then V to the gamma minus 1, V final, and then on the right side I'll have the initial. So P initial, V initial over NR, V initial to the gamma minus 1, the NR cancels, and then V final times V final to the gamma minus 1. How much is that? V final to the first power. V final to the gamma, right? Just add the powers. Gamma minus 1 plus 1, you just get gamma. So the final expression that I wanted to write, P final, V final to the gamma, is equal to P initial, V initial to the gamma. And this relation holds for what process? Adiabatic. Okay, let's stop here. We'll take our quiz. Do you want to stretch? Is anybody out?
Yeah.
If you want to start soon, we can start sooner, or we just start at the. If you want to stretch, do that. Let me turn the camera off.